right, buckle up, everybody, because today we're going deep, really deep, into the world of matter.
The stuff that makes up, well,
Pretty much everything, right?
you got it.
We'll be using some IGCSE chemistry study notes as our guide. But don't worry,
This is not your typical boring chemistry lesson.
no way.
Yeah.
We're on the hunt for some seriously cool, mind-blowing facts about solids, liquids, and gases, those fascinating states of matter.
Places matter.
The kind of stuff you'll actually want to tell your friends about, you know what I mean?
Absolutely.
It's kind of crazy how we see these states of matter all the time, every single day.
Right.
But we rarely stop to think, like, what's actually happening at the tiniest level, at a molecular level?
Yeah, it's easy to just, take it for granted.
Totally. Like, why does ice melt? Or how come we can smell those freshly baked cookies from, like, all the way across the room?
Uh-huh.
Trust me, once you get the mechanics of it all, you'll never look at a melting ice cube or a steaming cup of coffee the same way again.
I think you're right about that.
So, let's kick things off with a bang, shall we? Let's talk about the kinetic theory of matter.
All right, so the kinetic theory of matter basically tells us that everything, all matter,
Everything.
is made up of these tiny particles,
Tiny.
and they are constantly in motion.
Oh, wow.
Think of them as these super small building blocks constantly vibrating and bouncing and zipping around.
So they're like always on the move.
Always.
Right.
And how fast they're moving and how much freedom they have.
Uh-huh.
That's what determines if something is a solid or a liquid or a gas.
Okay, I'm starting to picture it now, these little guys just going wild.
Exactly.
So let's break it down.
Let's do it.
If we have a solid, does that mean the particles are like stuck in a rigid formation?
You got it. In a solid, those particles are packed super tight, they're vibrating, but not really moving around. They don't have that much freedom.
That makes sense.
And that's why solids have that defined shape
Yeah,
and volume.
like a rock or a block of wood or something.
Exactly.
Okay, got it. That's clear.
Right.
What about liquids then? I mean, they can flow, they take the shape of their container,
Right.
so their particles must be moving a little more freely.
Yeah, you're thinking along the right lines.
Okay, good.
They're still close together, but they've got enough energy to slide past each other.
Okay.
Imagine, a crowded dance floor
Oh, right.
where people can move around. They're not just stuck in one spot, but they're still bumping into each other.
Okay.
That's kind of what it's like for particles in a liquid.
I like that analogy. That's a good one. So there's movement, but it's still a bit restricted.
Exactly.
And then we have gases, where it's like the party's really started. Those particles are having a total free-for-all.
Precisely. In a gas, the particles, they're much farther apart,
Right.
and they move around randomly at high speeds.
So they're just like bouncing off everything.
Like imagine those bouncy balls in a lottery machine,
Okay.
bouncing off each other, bouncing off the walls of their container.
Yeah.
It's chaotic.
That's a good visual. So that explains why blowing up a balloon makes it bigger. We're basically injecting more of those energized particles
Uh-huh, those gas particles. You got
Yeah.
it, into a smaller space.
into that confined space.
Yeah.
This also makes me think about density.
Okay.
We know that gases are way less dense than solids and liquids, but what's actually happening at the particle level?
It all comes down to how close those particles are, how closely packed they are.
Okay.
So in a solid, remember they're crammed together,
Yeah.
so it's very dense.
Makes sense.
Liquid, there's a bit more space between them, so it's less dense.
Uh-huh.
And then a gas, tons of room to zoom around, lowest density.
So that's why a brick feels heavier than a balloon of the same size, right?
Mm-hmm.
Because those particles are,
Packed much more tightly together.
yeah, packed much tighter.
Yep.
Wow, it's amazing how something so tiny
I know, right?
can have such a big impact on how how matter behaves.
Absolutely.
Of course, there are always exceptions to the rules, right?
Mm. Oh, yeah.
Like water.
Water is a great example.
Water is denser as a liquid than as a solid, which is kind of weird.
Yeah,
That's why ice floats.
exactly.
But I've never really thought about why. Like, why is that?
Okay, so when water freezes, those molecules, they arrange themselves in a very specific way.
All right.
It's a hexagonal pattern.
Hexagonal fancy.
It is, and what happens is it creates more space between them.
More space between the molecules than in liquid form.
That's right, so that unique arrangement makes ice less dense than liquid water.
Huh. That is fascinating. So it's like that hexagonal structure is the ice's secret weapon
You could say that?
for being so buoyant, floating on top.
It works.
It makes you realize that even the smallest change, in that particle arrangement, can have such a big impact on how things behave.
For sure.
So speaking of change, how do we go from one state of matter to another? Like, what's going on at that molecular level when, say, ice melts into water?
So that's where state changes come in. And it all boils down to energy transfer.
Okay.
You heat a solid like ice, what you're doing is you're giving those particles more energy to move.
Right.
They start vibrating faster. Eventually, they break free from that rigid structure.
Okay.
And they transition into a liquid.
So melting is basically like giving those little particles a boost of energy to just loosen up and flow.
Exactly.
Okay, got it.
And the opposite happens when you cool a liquid down. The particles lose energy, they slow down, they settle back into that fixed structure.
And become a solid again.
Yep, we call that freezing.
So melting and freezing, it's all about adding or removing energy to change how those particles are moving.
You got it.
What about boiling? That's a much more...
It's definitely more dramatic.
Yeah, dramatic, like transition.
So when you heat a liquid to its boiling point,
Right.
the particles gain enough energy to completely break free from their bonds and escape into the air as a gas.
They just take off.
They're gone. Picture those dancers on a crowded dance floor just suddenly taking flight.
I love these visuals. Keep them coming. Okay, so boiling is like all those particles are just like, see ya, I'm out of here.
Exactly. It's a mass exodus.
Mass exodus. Okay, but what about evaporation? Isn't that also a liquid turning into a gas?
It is, but it's more of a gentler, slower process.
Okay.
Where those liquid particles at the surface, they gain enough energy to escape, but it can happen even below the boiling point.
So it's like if boiling is a mass exodus, evaporation is more like a few people sneaking off the dance floor to get some fresh air.
Exactly. They're slipping away.
Okay, I like that.
One by one.
What about the opposite then? When a gas turns back into a liquid, that's condensation, right?
You got it. Condensation is when those free-spirited gas particles, they lose energy.
Okay.
And they start clumping back together to form a liquid.
So it's like the party's over and everybody's heading back to the dance floor.
Exactly. They're getting tired. They're ready to settle down.
I love it.
Back to a liquid state.
Okay, so we've got melting, freezing, boiling, evaporation, and condensation, and they're all driven by changes in energy and how those particles are moving, which is just...
It's wild.
It's pretty mind-blowing, and this is happening all the time all around us.
Constant dance.
Yeah, from the ice melting in our drinks to those rain clouds forming in the sky.
It's amazing.
It is, it is. But it makes you realize that even though we think of matter as like static and unchanging,
right,
it's actually this dynamic.
It's always changing.
Yeah, ever-evolving system, really.
And what's really fascinating is how these tiny, tiny particles, these invisible things, can exert a force that we can actually measure.
And that's...
pressure.
Pressure. Okay, so we've talked about how those particles move.
Right.
But how does that turn into something like pressure, especially in gases?
Okay, think back to those gas particles bouncing around in a container.
Yeah.
Every time they hit the walls of that container, they exert a tiny force. And when you add up all those tiny forces, you get pressure.
So the more they're hitting the walls, the higher the pressure.
Exactly.
Okay, so what affects how often those collisions happen? Like, does temperature play a role here?
Oh, absolutely. Temperature is a measure of the average kinetic energy of those particles.
Kinetic energy, that's their energy of motion, right?
You got it.
Okay.
So increase the temperature of a gas, the particles are going to move faster.
Makes sense.
More collisions, pressure goes up.
So if I heat up a sealed container of gas, the pressure inside is going to increase because they're just bouncing around like crazy.
Exactly. They're energized.
Okay. What happens when we cool it down then?
Cool a gas down, the particles slow down, fewer collisions, pressure decreases.
It's like a molecular bumper car game. The hotter it gets, the wilder the ride.
The higher the pressure.
And the higher the pressure.
Exactly.
Okay, so what about the relationship between pressure and volume? Like if we cram those particles into a smaller space, does that affect pressure?
Absolutely. If you decrease the volume but keep the temperature the same, you're essentially forcing the same number of gas particles into a smaller space.
Okay.
More collisions.
So more pressure.
More pressure.
It's like squeezing a balloon.
Exactly.
Smaller the space, the more those particles bounce around, creating higher pressure.
You got it. And this whole interplay between pressure, volume, and temperature.
Yeah.
It's super important for understanding how gases behave.
It's fascinating, right? It's like this whole intricate dance of particles constantly interacting and influencing each other.
And we can measure it.
It makes me wonder, do those particles ever decide to move in a coordinated way? Like not just randomly bouncing around, but almost like a a choreographed routine.
Well, sometimes they do. It's called diffusion.
It's diffusion, okay.
And it's another really cool phenomenon that governs how particles behave, especially in gases and liquids.
Okay, I'm all ears. Let's hear about diffusion. What's going on there?
Okay, imagine you spray perfume in the corner of a room.
All right, I'm picturing it.
At first, you can only smell it right there.
Yeah, where you sprayed it.
But eventually, that scent fills the whole room, even if there's no fan blowing it around.
Yeah, that's true.
And that's because those perfume molecules are naturally spreading out
Oak.
from that area of high concentration
Oh, you sprayed it.
to areas of lower concentration.
It's like they're trying to even themselves out.
Exactly. It's a natural quest for equilibrium.
Equilibrium.
And this happens not just in gases, but in liquids too.
Oh, really?
Think of dropping a bit of food coloring into a glass of water.
Okay.
It slowly spreads throughout the water, even without stirring.
Because of diffusion.
That's right.
Wow, okay, so diffusion is happening everywhere.
It is. It's everywhere.
The air we breathe, the way smells travel, even how nutrients spread in our bodies, that's incredible.
It's all about those particles moving from high to low concentration.
So does temperature affect how fast diffusion happens?
Absolutely. Increased temperature
Yeah.
means those particles have more kinetic energy.
Right, they're moving faster.
Move faster, and that means faster diffusion.
So on a hot day, smells travel faster
Exactly.
because molecules are just like zipping around with more energy.
You got it.
What about the size of those particles? Does that matter?
You're full of great questions. And yes, particle size definitely matters.
Okay.
Turns out that lighter molecules, the ones with a smaller molecular mass,
Uh-huh.
they actually diffuse faster than their heavier counterparts.
So it's like a race, a cheetah versus an elephant.
I like
The
that.
cheetah's going to cover way more ground.
It's lighter, more agile.
Exactly.
Those lighter molecules can just zip around easier, and that leads to faster diffusion.
That's amazing. This whole hidden world of particle interactions is shaping our experiences in ways we don't even realize.
It's pretty mind-blowing.
We've covered so much already, from solids, liquids, and gases to these amazing processes like state changes and diffusion.
A lot of ground covered.
I feel like we've just scratched the surface, though.
You're right. There's always more to explore.
Is there more?
Well, did you know that under extreme conditions, matter can exist in states beyond the familiar solids, liquids, and gases?
Wait, there are more states of matter?
Oh, yeah.
I had no idea. Tell me more.
Well, buckle up because
Yeah.
next time
Yeah.
we're diving into some truly exotic states of matter
Okay.
that push the boundaries of what we thought was possible.
I am so ready for this. This deep dive is getting more and more interesting.
It's going to be a wild ride.
All right. I can't wait to see what other wonders await us in the world of matter.
Until then, keep those brain gears turning
Oh, they're turning.
and stay curious.
Always. All right. We'll see you next time, everybody, for part 2 of our deep dive into matter.
See you then.
Welcome back, everybody, to our deep dives into the world of matter. Last time, we took a pretty wild ride through the basics, right? Solids, liquids, gases.
The fundamentals.
Yeah, we even got into some seriously cool stuff like state changes and diffusion, all those tiny particles.
It's amazing how much we can learn just by looking at the world around us, you know?
Right, like melting ice, puddles drying up, it's all happening right in front of us.
Everyday phenomena.
Exactly, but like you were saying before, there's this whole other side to matter, this
It's a whole other realm.
yeah, this realm of matter that exists under extreme conditions,
Exactly.
pushing the boundaries of what we thought was even possible.
And today,
Gar.
okay, we're going there.
All right, lead the way.
So prepare to have your mind blown once again, because we're venturing into the extraordinary, starting with a state of matter that's actually more common in the universe
More common.
than all the solids, liquids, and gases we experience here on Earth combined.
Whoa. Okay, what is it?
A plasma.
Plasma. I've heard of it, but it always sounded kind of like science fiction to me.
It does have that ring to it.
Yeah. What exactly is plasma? And how is it different from the states of matter we talked about before?
All right, so think of plasma as like a supercharged gas.
Supercharged.
Okay. Where the atoms, they've been stripped of some of their electrons, so you end up with this mix of ions and free electrons.
So it's like a gas, but with an extra jolt of energy.
Precisely.
Yeah.
And that jolt makes plasma electrically conductive.
Oh, okay.
And it responds really strongly to magnetic fields, so it has some pretty unique properties.
That's fascinating. So where do we see plasma in real life?
Yeah.
I'm guessing it's not something I'm just going to find, like, lying around my house.
Well, you might be surprised. It's actually more common than you think.
Really?
Plasma is the most abundant form of matter in the entire universe.
Whoa.
stars, including our own sun,
Yeah.
giant balls of plasma.
Okay.
And closer to home, you've probably seen plasma in action as lightning
Lightning?
or those bright neon signs.
Wait, so lightning and neon signs, those are examples of plasma.
That's right.
That's incredible. I had no idea.
It just goes to show, even in the most familiar things, there's often this hidden layer of complexity
Right.
and wonder.
Totally. Okay, so we've explored this super hot world of plasma, but what about the other end of the spectrum?
Okay.
What happens when we go to the extreme cold?
All right, so when we get down to super low temperatures, we enter what's called the quantum realm.
Quantum realm, that sounds intense.
It is. Matter starts behaving in ways that, well, they defy our classical understanding.
Okay, can you break that down for me a little? What's happening in this strange cold world?
So imagine a group of atoms, and they've been cooled down so much that they've practically lost all their individual energy.
Okay.
They become incredibly sluggish.
Sluggish atoms.
They start to overlap and behave as one collective entity.
Oh, they merge together.
In a way, yes, it's called a Bose-Einstein condensate.
Bose-Einstein condensate. Okay, so it's like they're all part of one giant superatom.
It's a bizarre state of matter where quantum effects, usually confined to the microscopic world,
Right.
become visible on a macroscopic scale.
That is mind-blowing. So much we don't know. Before we go too far down this quantum rabbit hole, I want to go back to our IGCSE notes for a minute.
Okay.
There were some really cool examples of diffusion in action. I loved those.
Those were pretty vivid.
Yeah, especially that one with the potassium permanganate diffusing in water. What was happening there?
So you've got this beaker of clear water, right? And you drop a tiny crystal of potassium permanganate into it,
Potassium permanganate. It's purple, right?
deep purple.
Okay.
And at first, the color is just concentrated around that crystal.
Okay.
But then it slowly starts to spread throughout the water, creating this beautiful gradient.
So it's like a tiny purple explosion, but in slow motion.
I like that, a slow motion explosion. That's a good way to visualize it.
The IGCSE notes also mentioned another demonstration, this one using bromine gas.
Oh, yeah, that's a classic.
Tell me about that one.
All right. Picture 2 glass jars connected by a tube.
Okay.
One jar is filled with air, the other's got bromine gas in it, which is reddish brown.
Okay, so one clear jar, one jar with this colored gas.
Right.
What happens next?
When you remove the barrier between the jars, the bromine gas, it doesn't just stay put.
Yeah.
It starts to spread into the jar with the air.
So those bromine molecules are moving from where they're super concentrated to the jar where there's less of them.
Exactly. It's diffusion in action.
And does this keep going until both jars have like the same amount of bromine?
You got it. Eventually you end up with this uniform light brown color in both jars.
It's amazing how those gas particles just naturally mix, even without any stirring or anything.
It's all thanks to their random motion.
And that drive to spread out.
From high to low concentration, always seeking that equilibrium.
Right, equilibrium. We talked about that before.
It's a fundamental principle.
We also talk about how the size of those particles affects diffusion, right? Lighter molecules move faster than heavier ones.
Exactly. And the IGCSE notes have this really cool example using ammonia and hydrogen chloride gas.
Okay, I'm intrigued. What happens when those two gases meet?
They react to form a white, solid ammonium chloride.
So we start with two gases and we end up with a solid.
It's a classic chemical reaction.
Okay.
But here's the interesting part. The ammonium chloride doesn't form right in the middle where the two gases meet.
It doesn't. I thought they'd, like, meet in the middle.
You'd think so, but remember, lighter molecules diffuse faster.
Oh, right.
So the ammonia gas, which is lighter, it travels further in the same amount of time.
It's like that cheetah and elephant race again. The cheetah's going to get further faster.
Exactly. So the ammonia gas gets a head start, and that's why the ammonium chloride forms closer to the hydrogen chloride gas.
So it's all about that difference in their molecular mass.
Yeah.
Even though it seems like such a small detail, it makes a big difference.
Absolutely. It impacts chemical reactions and physical processes in all sorts of ways.
This is seriously cool stuff. It's like we're seeing this hidden world, this whole microscopic level of activity.
And it's happening all the time.
All around us. But understanding these basic concepts, it's not just for, like, appreciating science, right? This knowledge actually has some real-world applications.
Oh, absolutely. The applications are huge. They touch our lives in countless ways.
I'd love to hear some examples where is understanding states of matter actually making a difference.
Okay, well, let's start with something we can all relate to. Cooking.
Cooking. All right, I'm listening. How does knowing about states of matter make me a better chef?
Think about all the transformations that happen when you cook, right? You've got boiling water for pasta, melting butter in a pan, baking a cake.
Okay. Yeah.
These all involve changes between solids, liquids, and gases.
Right.
And they're influenced by things like temperature and pressure.
It's true, knowing how to control those things.
To make all the difference.
Yeah, knowing how to adjust for different altitudes, for example.
Exactly. And how different ingredients interact with heat, that's all chemistry.
Makes sense.
But it's not just cooking.
Okay, what else?
Medicine, for example.
Oh, wow.
Understanding diffusion is crucial for knowing how drugs are absorbed and distributed in the body.
That's a big deal, like knowing how quickly a medication will work.
Exactly. And environmental science.
Right.
Understanding the behavior of gases is essential for tackling problems like air pollution and climate change.
I can see that, knowing how pollutants spread, how greenhouse gases trap heat. It's all connected.
It is. And then you have materials science,
Material science.
where engineers are creating new materials with specific properties.
So like developing new alloys for airplanes or making those flexible plastics we use all the time.
Precisely. And it all comes back to understanding states of matter and how they behave.
It's amazing how this all starts with these basic concepts and then branches out into so many different fields
It's like a chain reaction of knowledge.
and innovation. I'm starting to see the world in a whole new light, seriously. But I have a feeling our journey's not over yet, is it?
You're right, there's one final chapter to this epic trilogy.
Oh, a trilogy.
We've got even more mind-bending states of matter to explore, groundbreaking research that's pushing the boundaries of what we thought was possible.
I am so ready. Bring on the final chapter.
Until then, keep exploring and never stop questioning the world around you.
All right, welcome back, everybody, for the final part of our deep dive into the world of matter. We've covered some serious ground, right? From the familiar solids, liquids, and gases.
To the fiery realm of plasma.
We even touched on those mind-boggling Bose-Einstein condensates.
It's been quite a journey.
But the adventure isn't over yet.
Not even close.
You mentioned some truly peculiar states of matter.
Oh yeah, we're going deep into the weird stuff today.
Okay, I am so ready. What mind-blowing phenomena are we tackling today?
Let's start with something that sounds like it's straight out of a superhero movie.
Okay, hit me.
Superfluidity.
Superfluidity. That definitely sounds like it has some superpowers.
It does.
What makes it so super?
Picture this, a liquid that flows with absolutely no resistance.
No resistance at all.
None. Zero.
So it could just, like, flow forever.
Pretty much, it can slip through the tiniest cracks, defy gravity, even flow uphill.
Wait, uphill.
You heard right, uphill. That's superfluidity in action.
That's insane. What's going on at the molecular level to make that happen?
It happens at extremely low temperatures, usually in liquid helium.
Okay.
When helium gets cold enough, the atoms basically become one giant quantum entity,
So they're all acting together.
moving in perfect unison.
That's so weird.
And that creates a completely frictionless flow.
So it's like the ultimate slippery liquid, like a master escape artist.
That's a great way to put it.
Okay, but beyond just being super cool, does superfluidity have any, like, practical uses?
Oh yeah, scientists are exploring its potential in all sorts of fields.
Like what?
Well, because superfluids have zero viscosity, they're incredibly sensitive
Sensitive to what?
to any kind of disturbance, so they can be used to create supersensitive detectors.
What kind of detectors?
Detectors that can pick up things like gravitational waves or tiny rotations.
Whoa, so they could detect things that are practically invisible to us.
Exactly.
That's incredible. And you mentioned quantum computing too, right? How do superfluids play a role there?
Well, quantum computers rely on those bizarre rules of quantum mechanics.
Right.
And superfluids, with their unique quantum properties, could help build the components for these futuristic computers.
So these weird states of matter could lead to some seriously groundbreaking technology.
Absolutely. We're just scratching the surface of what's possible.
Okay, so superfluids are pretty mind-blowing, but I have a feeling there's more, right? What other strange states of matter are out there?
Get ready for another one, Rydberg matter.
Rydberg matter. Okay, that sounds made up.
It sounds like science fiction, but it's real.
All right, what is Rydberg matter?
Imagine an atom that's been stretched out.
Stretched.
Yeah, with its electrons orbiting way, way further from the nucleus than normal.
So like a supersized atom.
You got it. And we can create this by zapping atoms with lasers.
So what happens when these supersized atoms interact?
That's where things get really interesting. They kind of blur the lines between a gas and a solid.
A hybrid state of matter.
You could say that. They're spread out like a gas, but they also have some structure, like a solid.
It's like they can't decide what they want to be.
Right. And we're still figuring out all the potential uses for Rydberg matter?
But it sounds like it could have some serious implications.
Oh, yeah, especially in quantum computing and sensing.
It's amazing to think that there's still so much we don't know about the universe.
Right.
This whole journey through the world of matter has been incredible. I feel my mind has been stretched, kind of like that Rydberg atom.
I think we all need a little mind stretching sometimes.
I agree. So to everyone listening, never stop being curious.
Never stop exploring.
There's so much out there waiting to be discovered, whether it's at the tiniest level or on a cosmic scale.
And the more we learn.
The more we realize how much we still don't know.
That's the beauty of it all.
And that's what makes it so exciting. So thanks for joining us on this deep dive into the world of matter. We'll see you next time for another adventure.
Until then, stay curious.